everyone, welcome to my civil engineering YouTube channel. Please subscribe to this channel and hit the bell icon to get notified when I post my new videos. Today I'll be discussing how to derive the bending stress equation. So here I have considered the beam which is subjected to bending. So this is the initial position of the beam. I have considered two sections here, AB and CD. So NN represents the neutral axis. So the distance between AB and CD is equal to delta x. The distance between the span between the two sections is equal to delta x. So after the application of the load, the beam starts to bend. After the application of the load, the beam starts to bend, which results in the deformation, so that the position of AB changes to A dash, B dash, and the position of CD changes to C dash, D dash. So I repeat it, after the application of the load, the beam starts to bend, which results in the deformation, so that the initial position of AB changes to A dash, B dash, and CD changes to C dash, D dash. So here as per the simple bending theory, so the top fibers of the beam will be subjected to compression, and bottom fibers of the beam will be subjected to tension force. So in this sketch, A dash, C dash, which is the final position of AC, is subjected to compressive force, and the B dash, D dash, which is the final position of BD, is subjected to the tensile force. So here this figure shows a small length delta x of beam which is subjected to simple bending. So due to the action of bending, the part of length delta x will be also deformed. So as I said that this delta x is the length between the two sections. So after the deformation, after the application of the load, due to the action of the deformation, delta x will also be, the length also be deformed. So that if I just project these line, the A dash and C dash line, if I just project this, so it meet at a point O. Let that it meet at a point O, so that let R is equal to the radius of the neutral axis. So R is equal to the radius of the neutral axis. Neutral layer, that is N changes to N dash. So initial position of the neutral axis is NN, and after the deformation it changes to N dash. So R represents the radius of the neutral axis layer, that is N dash. So next is theta. Theta is nothing but the angle subtended at O by A dash, B dash, and C dash, D dash, which are projected. So theta is the angle which is substituted at O due to projection of A dash, B dash, and C dash, D dash. Now if I just consider a layer EF at the distance of Y below the neutral axis layer NN, so after bending this layer, it will be elongated to E dash, F dash. So here you can just observe, I have just considered a layer here, this dark portion which you can just notice. So this EF is at the distance of Y from the neutral axis, below the neutral axis. So after bending, this was the initial position. So after bending, it changes to E dash, F dash, E dash, F dash, so which is elongated. So next is I need after bending, the EF changes to E dash, F dash, as I said that. So I can say that the original length of EF is equal to delta x. So since EF is the initial position wherein EF is equal to NN, that is the neutral axis layer, wherein before deformation that was the initial position. So EF is equal to it, we can also say that EF is equal to delta x. So Next, after the length of the also the length of the neutral layer. So as I said that since if EF is equal to delta x, so NN is also equal to delta x because NN is equal to EF. NN is equal to EF. This is at the initial stage. So after bending, the length of neutral layer n dash will remain unchanged. So after bending, so this is a final position, that is n dash is a final position of NN, wherein n dash is the final position of NN, wherein after bending also the length of the neutral axis will remain unchanged because as per the simple bending theory, it has explained that the neutral axis will neither subjected to compression nor tension. So with this assumption we will see that NN is equal to n dash means there is no elongation which is observed at the neutral axis level. So therefore I can straight away tell it as n dash is equal to NN, so that is equal to delta x because NN was equal to delta x. So after this, so as I said that n dash theta was the angle which was subtended at O. Theta is the angle which is subtended at O. So as per the arc theorem, so it is nothing but arc is equal to the product of radius and angle subtended. So with this mathematical theorem we can just directly state as n dash is equal to r into theta. So n dash is equal to r times of theta. So this is the due to the curvature of the circle. So next is after getting n dash is equal to r theta, so we want what is the value of e dash f dash. So similarly by following the arc theorem of the circle, we can straight away say that as e dash f dash is equal to r plus y times of theta, because the radius for e dash f dash is r plus y. So therefore, so radius into theta, so radius plus y times of theta. So next is as I said that n dash is equal to n, so that is equal to delta x, and also we said that n dash is equal to r theta. So straight away I can tell this as the delta x is equal to r theta. So delta x will be equal to r theta. So now I need to find what is increase in the length of EF. So that is nothing but increase in the length of EF is nothing but a final length minus that of the initial length. So I need the what is the rate of increase of the length in the layer EF, I need it. So in order to determine the rate of increase of the length of layer EF, so that is nothing but the final length minus initial length. So final length is nothing but E dash F dash minus initial length is EF. So if I just project that, so E dash F dash minus EF, so E dash F dash minus EF. So I know that E dash F dash is R plus Y times of theta. Just substitute that, and EF is nothing but R theta. So EF is nothing but R theta. So here EF was equal to delta x and delta x is equal to R theta. Therefore EF is equal to R times of theta. So if I just substitute and if I just simplify that, I will get the increase in length as Y times of theta. So this is how to determine the increase in length of the layer EF. So next is I need to determine the strain. So as I know that strain in the layer EF is nothing but increase in length divided by original length. So increase in length in the previous slide I have found it as Y times of theta, and original length is nothing but EF. EF is the original length before the application of load. So therefore y times of theta divided by EF. So EF was equal to r times of theta. So therefore after substituting it will become y theta divided by r theta. So y theta divided by r theta. Theta and theta get cancelled. So it is equal to y theta. So it is equal to y theta. So as r is constant, the radius is constant, hence strain in the layer is, we can straight away say it as strain in the layer is proportional to its distance from the neutral axis. So strain in the layer is proportional to distance from the neutral axis. So therefore it is equal to y by r. Strain is equal to y by r. So next is to determine the Young's modulus for the layer EF. So I need to determine the Young's modulus for the layer EF. So let F is the stress in the layer EF and E is the Young's modulus of the material of the beam. So therefore as I know that E is equal to stress in the layer EF divided by strain in the layer EF. So stress is as I said that it is equal to F divided by strain in the layer as I explained the previous slide. So it is equal to y by r. So therefore after simplification I will get the expression as F by y is equal to E by r. F by y is equal to E by r. So this is all about finding the Young's modulus for the layer EF. Since E and R are the constant, therefore we can say that stress in any layer is directly proportional to distance of layer from the neutral axis. So I repeated, stress in any layer is directly proportional to distance of the layer from the neutral axis. So next is we need to determine what is the amount of force at the neutral axis level. So neutral axis of any transverse section of a beam is defined as the line of intersection of the neutral layer with the transverse section. So therefore we know that F is equal to E by r into y. So in the previous slide we had determined that. So F is equal to E by r into y. So I have just taken a section here. So here I have just taken a cross section of the beam here, wherein NA represents the neutral axis. So NA represents the neutral axis, and I have also considered a small layer. So this is a shaded portion, the small layer, so which is at the distance of y from the neutral axis, and let dA is the area of that layer, this shaded layer. So I know the area of the shaded layer as dA. So in order to determine the force, I know that force on the layer is equal to stress into area of the layer. I know the expression of stress as force by area. So in order to determine force, it is equal to product of stress on the layer into the area. So therefore stress is nothing but F, and area of the layer is dA. So it is equal to F into dA. So I know the value of the stress as E by r into y. So E by r into y. So if I just substitute that E by r into y, so in this expression it becomes E by r times of y into dA. E by r times of y into dA. So this is the amount of force which is acting at the elementary strip of length of which is at the distance of y from the neutral axis. So if I want to determine the total force which is acting on the beam section, it will be obtained by integrating this equation. So total force on the beam section is equal to integration of E by r times of y into dA. So E and r is constant. So but we are going to determine this as this for the only for the bending. So we assume that this is a pure bending case. So therefore, if at all if it is a pure bending case, there will not be any existence of force on the section. So mind it. So if at all if it is a pure bending case, so then there will not be any existence of force on the section of the beam. So therefore I can just equate E by R integration of y into dA as 0. So therefore integration of y into dA is 0. So as E by R, it cannot be equal to 0 because it is not equal to 0. Therefore y into dA, it represents the moment of area dA about the neutral axis. Hence integration of y into dA represents the moment of entire area of the section about the neutral axis. But we also know that moment of any area of an axis which is passing through the centroid is always equal to 0. So hence the neutral axis always it coincides with the centroidal axis. So therefore the centroidal axis of the section, it gives position to the neutral axis. So this is all about the force in the neutral axis. So next we need to determine the moment of resistance. So due to the pure bending, the layers above the neutral axis, as I said, that it will be subjected to compressive stresses, and below the neutral axis the layers will be subjected to tensile stresses. So due to these stresses, the force will be acting on the layers. So this force will be having some moment about the neutral axis layer. So the total moment of these forces about the neutral axis for a given section is known as moment of resistance. So in the previous slide we have determined the force acting on the neutral axis, it was 0, but the forces but for the layers above and below the neutral axis, there will be some amount of force, there will be some creation of the force. So in order to determine the effect of forces, so we need to determine the moment of resistance. So moment of resistance is nothing but it is a total moment of these forces about the neutral axis for a section is called as moment of resistance for a section. So here I have considered a cross section of the beam. Again I have considered. So the force on the layer at the distance of y from the neutral axis is given. So therefore the force on the layer is nothing but at the distance of y from the neutral axis is nothing but E by R times of y into dA. So I need to determine the moment of this force about neutral axis. So it is nothing but force into perpendicular distance. So force of the layer into the perpendicular distance from neutral axis to that of the elementary step is y. So therefore E by R times of y into dA into y. So it is nothing but E by R into y square dA. So this is for the elementary step which is at the distance of y. So if I want to determine the total moment of forces on the section of the beam, so it is nothing but the integration of the above expression. So E by R times of y square dA. So the integration of y square dA is nothing but the moment of it is nothing but the moment of inertia. So the expression integration of y square dA represents a moment of inertia of the area of the section about the neutral axis. So therefore it is represented by I. So it is represented by I. So if I just furthermore simplify that, M is equal to E by R times of I. So therefore if I further simplify that, it will be equal to M by I, that is equal to E by R. M by I is equal to E by R. But in my previous explanation, E by R was equal to F by Y. E by R was equal to F by Y. So therefore M by I is equal to E by R, that is equal to F by Y. So this is all about the derivation of bending stress equation. Thank you for watching. Please like, share and subscribe the video. Thank you.